Under the Industrial Automation Laboratory,
I'll be explaining you how to use the PID controller block, which is a very powerful tool in any process control application.
now for a PID controller, the requirement is you will have analog input as input to PID controller, and the output of the PID controller will be in the form of analog. So let me pull here one block from analog input block, one analog output block, and then I'll go to control wherein I have a PID controller block. That means it could be related to the output from a temperature transmitter would be connected to analog input card of the distributed control system. From there it will go as a soft block as analog input, and I'll connect this to a soft block of PID. These are the soft links which I am using. Then most important part of this exercise is to configure a PID controller. So right click on this and configure. Description could be a PID, maybe first PID of the plant. Mode type, if I click here, either you can use it in auto mode or in manual mode. That means if the PID controller is to be bypassed, you can take it in manual mode and increase or decrease the output value without PID controller. That's the reason the option is given. So let me select auto. The moment I select auto, action type and controller type will be visible. Select action type. There are two types available. One is called as direct acting PID controller and other is called as reverse acting PID controller. By definition, if the output of the PID controller is increasing, if error is increasing or vice versa, it is called as direct acting PID controller. Whereas if the error is increasing and the output of the PID controller is decreasing or vice versa, is called as reverse acting. Let me select direct acting.
I have a choice, and this can be exercised or executed based on the type of final control element which you have chosen.
That means what type of control valve have you chosen, whether it is air to open or air to close. Based on that, action of a PID controller can be decided. Now, controller type means the algorithm which you will be running inside a controller, like P or P plus I or P plus D or P plus I plus D. That means the actions which you will be using, you can use only P controller or you can use only P plus D controller. For demonstration, let me select P plus I plus D controller. The moment I select controller type, the PID algorithm window would be open. So there are two types of PID controllers available. One is called as non-interacting type of a PID controller and other is called as parallel PID controller. The entire information about this algorithm under the heading of non-interacting or parallel is given in theory of PID controller of this experiment. So if I select non-interacting type, then I can select set point value which can be from 0 to 100%. These are all normalized values. Normalized means if the temperature is 0 to 200 degrees Celsius, the transmitter will give you output from 4 to 20 milliampere. That 4 to 20 milliampere output would be converted into 0 to 100%. So in other words, if your controller output or the controller input is being shown as 50%, that means currently the temperature is 100 degrees Celsius. That's the meaning of the word normalized value. So I'll select the set point as 50%, max value and mean value. That means when a PID solves the algorithm, the output of a PID controller can be in between 0 to 100%. But while configuring the PID controller, I have a choice to select this value. Maximum value I can select 100%. But if I don't want that final control element to totally open, I can block it or I can lock it to 80%. I can lock it to 90%, or I can lock it to a value which is desirable for my application. That's the reason this configuration is given. Similarly, if you don't want to close the control valve fully, even if the PID controller output is 0, you can lock it to some minimum value. So you can set that minimum value using this.
Now, there are three important configurations: KP, KD, and KI.
Now these values are basically KP, KI, KD configurable values of a PID controller. Depending on the requirement of the plant, PID controller needs to be tuned. It's called as tuning of a PID controller. So in other words, tuning of a PID controller means identifying optimum values of KP, KI, KD, like KP, KD and KI, and the proportional bias is called as tuning of a controller. Proportional bias means output of the controller when error equal to 0. So once the error is 0, E equal to 0, controller should give you some output depending on how much output you have to continue feeding to the final control element so as to maintain this set point equal to process variable. Now this can be found from various methods of tuning a PID controller. So you can set this value, you can set this value, and initial controller output for the academic purpose, we have kept this configurable initial controller output where you want to avoid a bumpless transfer. For example, I can put this value in between 40 to 60 as it is mentioned here. So I have kept it 40. Scan time is 1 means as this is a simulator, you need to know every after how much time the PID controller value is going to be updated. It's called as a scan time of a PID controller, and you can set scan time from 0 to 5 seconds. I have kept it as 1 second. This is one way to configure a PID controller, and you can submit. You can change the values and you can submit. For example, let me put it proportional bias as 50 means the controller output at error equal to 0 would be 50. I'll submit this. The moment I have configured this PID controller, then I can compile this program. I can start running this program. Now what will happen? The analog input is 0, and that's the reason controller output is 100%. Now if I change analog input, as this is a simulator, physical process is not connected to this, so I do not know what will be the dynamics of the input side. So I'm just putting some values just to get a feel of how PID controller behaves. For example, instead of 0, if I write here 50 and I submit, what happens is your PID controller will start performing and the value of the output will be changed. Now as I have changed the value of input, the PID controller will start giving me the output, or the output of the PID controller is changing. Now the reason for this is I will change this value suppose to 80. Let's see what happens. The moment I change this value to 80, again PID controller will go to the other side. Now instead of decreasing the value, now the value is increasing. Instead of that, if I again make this value equal to 10, that is 10%, set point as 10%, this value will go on decreasing.
This is how you can test a PID controller.
Now, an exercise for you is to test the output of a PID controller for various values of KP, KI, KD, and the set points, and the action, and the algorithm, and the bias value. The theory associated with this PID controller is already shared in the tab theory of this experiment. Thank you.